All right, so continuing on with our graph theory, this is some more graph concepts and terminology. This would be section 5.3. All right, so adjacent vertices are two specific vertices that are joined by an edge. A loop is adjacent to itself. So if you remember back when we did loops, down here in the corner here, E would be adjacent to E. All right. If an edge exists between two vertices, then they are adjacent. So if there's an edge, they're an adjacent. So is AB adjacent, or is A adjacent to B? A adjacent to B? Yes, it is. Okay. Example 2 here. Is E adjacent to itself? Yes, because we have our loop right here. So it'd be adjacent to itself, even though it kind of got cut off of my paper. It would be adjacent to itself because there's my loop. So yes. Is D adjacent to A? Does D at all connect to A? So no, they would not be adjacent. There is not an edge that goes directly from D to A. Is C adjacent to itself? Is there a loop at C? No, there's not. Remember, only loops are adjacent to itself. So, I mean, I could maybe get back to C, but it's not necessarily adjacent to itself. All right. Now, adjacent edges are two edges that intersect or share a vertex, or intersect at a vertex. They share the same vertex. So is AB adjacent to BC? AB, there's BC. Yes, because they share vertex B. Okay, and you can kind of tell in the name, AB, BC, they both share B. Okay, but now is CE adjacent to BD? No, they are not adjacent to one another. All right. So just some terminology there. So now the next thing is the degree of a vertex. So if I ask you what the degree of a vertex is, it is the number of edges at that vertex. So degree A, this would be basically a notation. So if you see DEG A, they want to know what is the degree of vertex A. And in this case, vertex A, the degree would be 1. There's just one edge coming into vertex A. So a couple things. A loop would count twice. So like at E, this loop, I would count that as 2 when it comes to the degree. An odd vertex is a vertex that has odd degree. And an even vertex is basically a vertex that has even degree. All right, so find the degree of each vertex. So let's start with the degree A. And what is that? Well, we already said that was 1. All right, what about degree B? And like I said, you just kind of go to that vertex and then you just count how many edges come into it. So 1, 2, 3. So degree B would be 3. Degree of C would be what? 1, 2. There's only 2 edges that come into C. What about D? Degree of D would be 1, 2. And then the degree of E would be, so once again, at E, there's 1, 2, 3, 4. Remember, a loop counts twice, so there would be a 4. Okay? That would be the degree of each vertex in figure 1. All right, questions there. So degree is just how many edges come into that vertex. All right, now, a path. A path is a sequence of adjacent vertices from a starting point to an ending point. In a path, each edge can be traveled only once. So once you go over it, you can only do that once. And the length of a path is the number of edges in that path. So our first example here then would be to find a path from A to E. So how can we get from A to E? Well, we would list it as, so our path from A to E, we would go from A, we could go to B, we could go from A to B to what? D to E. That would work. That would be an example of a path. A, B, D, E. Is that the only path? No. We could have said it is A, B, C, E. Okay? A, B, C, E would also be a path. So just because, they just wanted to know a path. In some instances, there could be more than one path. And there might be some more directions on, like, I don't want you to hit this, or I want you to hit this. Those would all be things that we would take into consideration in coming up with our path. Okay? So there's a path. It's a sequence of adjacent vertices from a starting point to an ending point. The only trick is that you cannot go over an edge more than once. All right. So the next word then is a circuit. And basically, paths and circuits are very similar. The only difference is a path, the starting point and the ending point are not necessarily the same. Whereas a circuit, which if you really think about it, they're saying a circuit is a path, so it's a special kind of path. The only difference between a path and a circuit is that it starts and ends at the same vertex. Okay? So you have to get back to where you started. That is kind of the difference between a path and a circuit. So a circuit is a special kind of path. You just have to get back to where you started. And so my example here, let us find a circuit for C. Okay, so let's get back to our picture here. What would be a circuit for C? I can start at C, and I need to get back to it. So what could I do? Well, I could do C down to E, up to D. So we could do C to E to D, down to B, back to C. Would you agree with that circuit? All right. C, E, D, B, C. There's my circuit. Is it the only one? No. I could have gone the other direction. I could have thrown my loop in there and said C, E, E, D, B, C. So once again, I think part of this is going to be, we talked about it earlier, finding the shortest route. So maybe that's where you would not do something. But also, if they wanted you to like maximize the number of edges, or if we were talking this in real life, maybe like roads that you were on, then you would need to add more to it, or go a different direction, or count that extra loop. So it really is going to kind of depend on what they want us to do, and that's some things we're going to talk about. Right now, we're just talking about the terminology. We're going to talk about there's different kinds of circuits. So we'll come up with that a little bit later. All right. So take a minute. They want to know a circuit for E. Okay. What's a circuit for E? All right. Well, like we said, so you could just say E to E like that loop, and that would technically be a circuit. But now, once again, if they wanted you to do a little bit more, then you could do very similar to what we did with C. We could start with E, go to D, go to B, Now, why am I not going to A? Well, what's the problem? Remember, we're not supposed to repeat an edge. So if I go out to A, am I going to be able to get back? No. So without crossing it again. So that doesn't work. So we could do E, D, B, C, E. That would also work. Okay. So we could say it was E to D, B, C, back to E. Okay. That would be one of my examples of a possible circuit. All right. Questions there? All right. So what I would like for you to do for your homework on this lesson is I want you to look at practice with figure 2 here. Okay. I want you to do that for part of your homework. All right. Any questions about that? All right. So now moving on. A graph is connected if any two vertices can be joined by a path. It is always possible to travel from one vertex to another vertex in the graph. If this is not possible, then the graphs are disconnected. The connected parts of the disconnected graphs are called the components. All right. So real quick, you can see this is kind of an easy. This would be an example of the connected. Notice that you can, without lifting your pencil, hit all of your vertices, correct? That'd be kind of a good way to think about it. Can I, even now this one, kind of ignore the whole thing, not touching it again, but could I touch everything with my pencil without lifting up, or in this case my finger, without lifting up my paper? Yes, that makes it connected. But notice over here, here's all my points, but if you notice, like I can do this, but is there any way for me to get over to that other picture? And that would be no. So this would be an example of disconnected. These are connected and these are connected, but my picture as a whole is supposed to be all of those. And there's no way for me right now, there's no edges connecting these two. Okay? All right. And so that would be sort of where we would need what we call the last kind of bit of terminology here in this lesson, and that is a bridge. A bridge is an edge in a connected graph who, if you took it away, would make it disconnected. An edge that is also the only path between two vertices. No alternative routes exist to travel between two vertices besides that edge. Would make it a bridge. So let's go back here then. Let's talk about a bridge. Example 1. Let's go back to graph number 1 here. So what would be an example of a bridge with graph number 1? Here was graph number 1. What would be an example of a bridge? Well, if I took BE out of the mix, would those graphs be connected anymore? No. Okay? That would make BE a bridge. Now, if I took out FB, would that be a bridge? No, because I could still have everything else connected without that. All right? So, same thing here. You know, what would be now? So basically, an example of a bridge is any edge really that connects just one thing. So, like if I took SW out, then S would be out here by itself, and the rest would be connected. If I took TW out, then that would be a bridge because then this would be by itself, and this would be by itself. So it would unconnect them, even though this is already unconnected. But those would be examples of bridges. Okay. Now, if I took RX out, that's not a bridge because R and X would still be connected, okay? So that is what a bridge is, okay? All right, questions there. So the other part of your homework then for this lesson, I would like for you to do the rest of this page. So I want you to find the bridge practice, and you're going to do figure 1 and 2. Figure 2 and figure 1 from the beginning, and then you're going to draw given these examples, okay, or given this set of circumstances, okay? That is going to be your homework. So bridge practice down to the bottom, okay? Any questions on 5.3? All right, that is your homework for 5.3.